Review problem number 2. Find the equation of a linear function containing the points 7, 2 or 7, 9 and 10, 11. Give an example in the real world that this function could model. So it says that we have this linear function. So beginning from that, we have to start with the 2 points. We have 2 points, 7, 9. So our first point is 7, 9. And our second point is 10, 11. So knowing those 2 points, we will have an equation in terms of A and B. But we have to know, or we have to completely comprehend and also memorize the function or the general form of a linear function. And the linear function has the general form ax plus b, where our a is the slope. This is the slope of the linear function. And b is the y-intercept. Or this b is the point where your x is 0 and you have a certain value of y and it crosses your y-axis. So having this general form, we could now get 2 functions or 2 equations with 2 unknown variables a and b. So the first point 7, 9 will yield us, working on this general form itself, our 9 is the y and our x is 7, so that gives us 7a plus b. And with the second point 10 and 11, our y is 11 and our x is 10, so that will give us 10a plus b. And we could use division here. So division of the equations, that's 2 minus 1, in order to isolate one unknown variable from the other, or completely obliterate the other variable, so that all that is left is either a or b that we could work on, so we could find its value in terms of the numerical values. So in this case, what we're going to do is to subtract 1 from 2. So 2 minus 1 then would give us 2, which is equal to 3a. And this is completely obliterated. This is completely taken out of the equation. And this will give us a value of a, which is 2/3. Okay? And with this value of a, we could now solve for our b by choosing whatever equation of the 2 equations here would be ideal or would be comfortable for you to solve. So in my case, I'm going to choose number 1. And in this case, my a is 2/3, so let us write the equation again. Our equation is 9 is equal to 7a, and our a is 2/3 plus b. Now you could see that we could work on b now. So we could find its value by transposing this term here on the left and rearranging the positions. Our b now is on the left side, and these expressions containing 9 and 7 times 2/3 would be on the right position. So our b here would be 9 minus 14 over 3. And working out with fractions, we have to multiply 9 by 3. 9 times 3. And because we multiplied it by 3, we could also divide it by 3. And this is just emphasizing the LCD of the 2 terms here with a fraction as one of the terms. So our b hence would be 27 7 over 3 minus 14 over 3. So our b would give us 27 minus 14. So if you have the same denominator, you can now combine the numerators. So this will yield us 27 minus 14. So that's 13 over 3. Okay? So our b is 13 over 3. And our a here is 2/3. And our function then would be y, or f of x, is equal to, what is our a? Our a, or the slope of this linear function, is 2/3. 2/3 x plus 13 over 3. So our y-intercept is 13 over 3, meaning that it crosses. This line has a y-intercept, or the graph crosses the y value, or the y-axis, at the value y is equal to 13 over 3. Okay? Give an example in the real world that this function could model. There are many examples out there. So you could do your own research, or you could do your own observation. And one example could be the population of a certain subdivision, for example. So if in case that this subdivision is constantly, it has a constant increase of 10 houses per month, so there are no deviations from the 10 houses. So next month there would be 10 more houses, and the next month is 10 more houses. So if it's a pretty standard of the subdivision to increase, or to have 10 houses every month, then it could be taken as a model for this linear function. Other examples are out there, and they could be pretty much diversified. So you could give whatever example you want. Okay? For letter B, sketch two graphs showing a decreasing exponential function and an inverse variation power function. Give two ways in which the graphs are alike, and give one way in which the graphs are different. So for number 2, or for letter B, I will have to choose, my exponential function would be y is equal to 2x, and my inverse power function would be y is equal to 1 over x squared. That's pretty much an inverse variation power function. So for the first function, I will have to create a table, okay, just to show you the difference in the x and y values. Okay, so but in the end, this exponential function would have an asymptote at x is equal to the x-axis, okay, or y is equal to 0. That's what I meant. Okay, so x, this is my x column, and this would represent my y column. So I'm going to choose from -2 to 2. Okay, and in this part we have the inverse variation power functions. So I would also want to show you the table, a tabular representation for this function, and let's see what happens. And I'm going to choose the same domain. So this is my x column, and this would be my y column. So let us do the tabular interpretation together, and let's have a help from our calculator. So if my x is negative 2 here, that would give me 2 raised to negative 2, or that's pretty much 1 over 4. And 1 divided by 4, or 1 over 4, is 0.25. So we have 0.25 here. If my x is negative 1, that would give me 2 raised to negative 1, or that's 1/2. So that's 0.5. So 0.5. If my x is 0, then this is 2 raised to 0, and that gives me a simple 1. And if my x is 1, that equation will give me 2, and this function will be 4 at x is equal to 2. Now in the case of this equation, 1 over x squared, if my x is negative 2, so I will select from negative 2 to 2 also, so that they have the same domain. So in this equation, I will have, for x is negative 2, I will have 1 over 4. So that gives me 0.25 in here. If my x is 1, or negative 1, that would give me 1. 1 over 1 squared is just 1 over 1, and it's 1. If my x is 0, then I will not have any value at this point, because it is undefined. If my x is 1, that gives me 1, and if my x is 2, that gives me 1 over 4, or 0.25. Okay? So now let us have a graph to differentiate each. So this is for the graph of the first function. So this is for a. Y is equal to 2 raised to x. This is for my exponential function. This would be my y-axis, and this would be my x-axis. Okay, and this equation, y is equal to 1 over x squared, will have this graph. Okay, here. So let me use this axis. So I'm graphing my y is equal to 1 over x squared here. Okay, y is equal to 1 over x squared, which is an inverse variation power function, which is the inverse of a quadratic function, the most basic quadratic function, 1x squared. Okay, so now let me have my labels. So this is 1, 2, negative 1, negative 2, negative 2, negative 1, 1, 2, and this is my y value. These are for my values of y. So I will have to label 1, 2, 3, 4, 5. Okay, let us begin with the power function, or the exponential function rather. If for the exponential function y is equal to 2x, 2 raised to x. If my x is negative 2, that's negative 2, 0.25. So it's here. The graph is here. Okay? And then it becomes 0.5 at this point, negative 1 is 0.5, and it will have a y-intercept at y is equal to 1, and then if it's 1, we have 2, and then if we have 2, then this would be 4. And if you get larger or more negative values of x, you could notice that this will approach this x-axis, but it will definitely not reach the x-axis. So this is our asymptote. Y is equal to 0. Okay? So the graph of this function would be like this. Okay? So it's an exponential function. It is concave up. These are the properties. It's concave up. And increasing. Okay, and has an asymptote at y is equal to 0. That's the asymptote. Or y is equal to 0 is just the x-axis. Okay, now we go to the next function, y equals 1 over x squared. Notice that it has an asymptote at the x-axis also. So this is the asymptote. Y is equal to 0. So let me label this graph here. So this is 1, 2. This is negative 1, negative 2. 1, 2, 3, 4. These are the y values. 1, negative 1. Negative 2. It's pretty much big. So negative 2, negative 3, negative 4. Okay, so this is my power function. If my x is negative 2, then my y is 0.25, so which is here. If my x is negative 1, this is 1. If my x is 0, it's undefined. And if my x is 1, it's 1 also. And if my x is 2, that's 0.25. So note that we have an asymptote at the x-axis. At the same time, so this is x and this is y. At the same time, we have another asymptote at the value x is equal to 0. So this is x is equal to 0, which is also equal to the y-axis. Okay, so there are two asymptotes here. We have the y-axis and we have the x-axis. And if we are to graph our function, then because we have an asymptote here at the y-axis, it won't touch your y-axis. At the same time, the graph won't touch your x-axis. So this is the graph. Okay. So this is my graph for y is equal to 1 over x squared. Let's make it clearer. So 1 over x squared. Okay, now what are the similarities in here? Number one similarity is that they have an asymptote, a horizontal asymptote at y equals 0. So this is their horizontal asymptote. What else? This graph here has a concave upwards and an increasing property, which is similar to the behavior of this graph. This graph, which is just one part of our power function, inverse variation power function, is also increasing and is also upside down. What I mean is it's increasing at the same time it's concave up. So those are the similarities. Okay? The differences are more. So the second similarity is one part for power function, y equals the inverse of the power function, 1 over x squared. One part of the graph behaves like the exponential function. Okay. And what else? Do we have other similarities? No more. Okay. But the differences are more than their similarities. So for example, the number one difference is that this function here has only one graph. Okay? And it does have a y-intercept. So its y-intercept is taken here at this point. Okay? And what is the y-intercept here? The y-intercept is at 0, 1, meaning when y is equal to 1, your graph touches the y-axis. Okay? But in this case, we don't have a y-intercept because definitely y-axis or x is equal to 0 is an asymptote itself. So this restricts the graph of this function, the inverse variation power function, because your graph could not touch the y-axis at the same time that it couldn't touch the x-axis. Okay, and that's another similarity, because in this exponential function we only have one graph, and in here we have a pair of graphs. These two curves are restricted to touching the x-axis and the y-axis. So in this case, we have two graphs. Okay, we have two pair of graphs, and the other one is concave up, but it's decreasing. So here it's increasing. The graph is increasing here, increasing, and concave up. But in this case, this is decreasing, although this is still concave up. Okay? So those are the differences and similarities of these two equations.